Here is section 3.5 in calculus. We're summarizing the sketching of a curve. So polynomials, here's the things that you want to do if you're asked to graph a polynomial, and we'll go over rationals in a little bit. So polynomials want to find the maxes and mins. So that means we're going to be taking the derivative, setting it equal to 0, finding those x's, and then taking those x's and plugging them back into the original in order to find their y values. And then identifying increasing and decreasing. Well, we can go ahead and put that on those x's that we just found from our derivative, putting those on a number line and testing points in between, and that will tell us whether it's increasing or decreasing between those maxes and mins. And then we want to find inflection points. In order to do that, we got to take the second derivative, set that equal to 0, put that on a different number line, test points in between those into the second derivative, and if it's positive and negative on each side, then it has an inflection point, and you can also identify the concavity that way. And then you can go ahead and sketch those points for your graph. Okay, and so remember, anytime you want your y values, you have to take these x's that we find and plug them back into the original. Okay, so let's go ahead and start graphing some polynomials. So here's a polynomial, 1 plus 3x squared minus 2x cubed. So we can know from the beginning that it's an x cubed, so it's going to look either like this, something like this, or because this is negative, it's actually going to look like this. So we know the end behavior, right? As we throw in bigger and bigger negatives in here, this is just going to go to positive, so it's going to increase like this one. And as we throw in bigger and bigger positives, cubing those times by negative is going to go down. So we know what the ends are going to be like. So now we just need to know what's happening in between, here. So that's when we take the first derivative, and so that would be 6x minus 6x squared. So we could factor out a 6x because we want to take our derivative and set it equal to 0. So that means this is 0 or x equals 1. That would make these 0. So those are our x's that we're going to put in a number line. And since we do want the maxes and mins, we go ahead and plug these points back into the original in order to find what the y values are, so that we can actually graph these 2 points. So we plug in 0, and we get 1, of course. So I have this point 0, 1. Don't know whether it's a max or min yet. That's where I kind of put them on a number line and test. And then I plug in 1, so I plug 1 in. And when I plug in 1, I can just plug in 1 and evaluate, or I can do synthetic division. All right, 3, 2, 1, 0. I'm talking about exponents there. So 1 would go in the box. What's nice about 1 is really you don't have to do synthetic division. All you have to do is just add up. So we get 2. So those are my 2 points that I could plot on a graph. Whenever you plug in 1, all you have to do is just add your exponents. 1 plus 3 is 4. 4 minus 2 is 2. But you can do synthetic division, or you can plug them in and evaluate. So we're going to take those x's, 0 and 1, put them on a number line, and we're going to do increasing and decreasing test. So what this means is that I'm going to test points in between and after, so to see where it's going up or going down. And we test these points to the left and to the right into the derivative. So how about -1? This one stinks because it's a half, but that's okay, and say +2. So we plug those into the derivative, which was 6x, and it's better in factored form because then evaluating is a little bit easier. You don't have to square anything. So when I plug in a -1 in here, -1 here, -1 here, this whole thing's going to be negative, and this will be negative, and a negative times a negative, it will give me a positive, so I know it's positive here. And then I'm going to take that derivative and plug in 1/2. That's why these are really good in factored form, because I'm just multiplying factors here. So 1/2, I know it's going to be positive, or sorry, I know it's going to be negative. A half minus 1 is negative, and this is going to be positive. So positive times a negative is a negative. So we know we're negative here. And then again, I can plug it in to this last one. Plug in 2, positive, plug in 2, positive, 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 times a positive is positive. So we know because we are decreasing where it's negative, so that means between 0 and 1, between these maxes or mins, we are decreasing. And then we're increasing from negative infinity up to 0. So negative infinity up to 0. And you could do brackets on these if you wanted to, because it takes up the domain. And the domain of almost all polynomials from negative infinity to infinity. And then after 1, it also increases. So our graph looks something like this. We are increasing, then we're decreasing, and then we're increasing again. Not quite. Increasing to there, decreasing, keeps on decreasing till here, and then it starts increasing. So that means we have a max at this point. So the 0, 1 is a max. So 0, 1 is a max. And the minimum, because we're decreasing and then increasing, our local min, we have a local min at 1, 2. So we can graph those points. Our max at 0, 1, so that means our x is 1, or x is 0. We have a max, and that point is 0, 1. And our minimum is at x equals 1. Again, we plug these back into the original in order to find their y's. That's what we did earlier. And so that's how we can use the first derivative test and the increasing decreasing test to find those max and mins. Another way to find your max and mins is to take the second derivative, So we take the second derivative, and we take that second derivative, so that would be 6x is our first derivative. And we get 6 minus 12x equals 0. Set it equals 0. Add 12x to both sides, so that would be 1/2. So x equals 1/2. So we don't really need to set this equal to 0 for our second derivative test. The second derivative test is another way to find maxes and mins. So which means that you take the second derivative, so 6 minus 12x, and then you take these x's, 1 and 0, and you plug them into this, and if you get a positive, that means you have a local max. So if you plug in 0, we would get 6, so that's a positive, so a max. And if I plug in 1, I would get a negative, so that means I would have a minimum, which we can see that we did. So the second derivative test allows us to find maxes and mins. But what we're going to use, since we already found the maxes and mins, we're going to use the second derivative to test for concavity and to find inflection points. Okay? So we put this, take our second derivative, set it equals 0, find our x, and then I'm going to test to the left of that. So how about 0, since we already know what that is, positive. And to the right, which is 1, so I can know what that is as well, that's negative. So what that tells me with the test for concavity is that I'm positive from negative infinity to 1/2. So that means I'm concave up, so that means my u is facing up. And then I'm concave down because it's negative after that, from 1/2 to infinity, so that's concave down, so the u is facing down. And whenever it switches to concave up to concave down, or from concave down to concave up, you always have an inflection point at that. So I have an inflection point at x equals 1/2. So if I want to find the y value, I need to plug that back into the original. So negative 1, 2, 1, 1, 1/2. 1 plus a half is 3/2. So I have this point 1/2, comma 3/2. So now I have a local max, local min, an inflection point, and I know what's happening at the end behavior. Another thing we kind of look for when we're graphing these is what our x-intercepts are. And we do that same way as we did at pre-cal. We use syntactic division. We find our factors of our constant, which this one would be 1, and we take our lead coefficient, the factors of that, and we run them through synthetic division until we can find a couple, and then we can break it down from there. So we want to find those X-intercepts as well. But we can go ahead and graph our local max at 1, 2. So at 1, 2, our local min 0, 1, and then our inflection point in between, and then we can go ahead and graph from there, because we know what's happening to the left and we know what's happening to the far right. So we have our graph. It looks something like that. So the only thing added to this might be finding those X-intercepts. Okay, so rational functions, we did this also in pre-cal. I guess it's harder, sure. And we want our asymptotes, right? So to find the asymptotes, we want to find the horizontal and the vertical. So the horizontal is, well, it can be tougher, because sometimes it all depends on the degree of the numerator and degree of denominator, which we'll talk about. And vertical asymptotes, that's when we set our denominator equal to 0. We don't care about the numerator. So we set that equal to 0 and then solve for x's. So and then we check for maxes and mins, do the same thing as test as before, and then we set up increasing and decreasing, find out concavity, and then test those points. So this, what was hard maybe in pre-cal, is actually the easy part. And then here is the little bit harder part, because this is where you have to take the first derivative and the second derivative, which is a fraction's a little bit harder, right? Because as we look at rational functions, they're fractions. All right, and then we just want to check with our asymptotes, with our concavity, make sure everything's okay. Okay, so first thing we want to do is find those asymptotes. And first vertical asymptote, we set the denominator equal to 0. So we take x squared minus 1, set it equal to 0. We get x squared equals 1, square root, so we get x equals plus or minus 1. So those are our vertical asymptotes. And the only thing you need to make sure is when you plug them in, if you plug these into the numerator, that it doesn't cancel out or anything like that. So what I mean by that is that if I plug in 1, positive 1 in my numerator, I don't get 0, and I plug in negative 1, I don't get 0. So if anytime you plug in one of those into the numerator and you get 0, that means you have a hole, where with these two, I have vertical asymptotes at those x's, positive 1 and negative 1. So what that means is basically that if you would plug in one of these into the numerator and you get 0, what that means is eventually you could probably cancel out something, so that it would simplify, kind of what we did when we took the limits and we factored those, then we canceled out like factors, that kind of thing. So right now I have vertical asymptotes at those two x's. So horizontal asymptotes is basically what means when we take the limit as x goes to infinity, right? As we get bigger and bigger and bigger, what's our y values? What's happening to our y values? So we could just go ahead and take this limit, which we've done before, right, back in chapter 1. And so this one we can't cancel out, we can't factor out, right? So this one I can just plug bigger and bigger numbers in, see what happens. And basically this one's not going to matter, right? And these x squareds are going to cancel out. So really this is just going to equal 2. Because this one, as this grows more and more and more, this one's really not going to matter, right? And this is what we talked about in pre-cal, where we said look at the degree of the numerator and the degree of the denominator. If they're the same, you just divide the lead coefficients, right? If the denominator is bigger, so if we had x over x squared, that means that the denominator degree is bigger, because these would basically cancel out, and I would have 1 over x. And as I plug bigger and bigger numbers in here, right, plug in 10,000, right, this is approximately going to go to 0. So whenever your degree of the denominator is bigger, it's going to go y equals 0 is your horizontal asymptote, where this one is y equals 2 is our horizontal asymptote. And then if the numerator is bigger, this is the only problem. When the numerator is bigger, that means that you're going to have to actually divide it out, because you're actually going to have not a horizontal asymptote, but you're going to have an oblique asymptote, a diagonal one. So that's where you actually have to divide this out, like long division. Okay, so now we have a horizontal asymptote, and we have our vertical asymptotes at 1 and at negative 1. And so now we need to find our maxes and mins. Well, that's when we got to take our first derivative, right? and set that equal to 0 and find our x's. So here is the hard part because we have a quotient. So that means we have to do quotient rule. So I got to take, here's my f, here's my g. I got to take the derivative of f, which is just 4x. I got to take the derivative of g, which take the derivative of g, not g squared yet. That's just 2x. And then I got to take g squared, which is just this squared. All right, so then it's g times the derivative f. So g times the derivative f minus f times the derivative of g all over g squared. So the tricky part is now we're not just looking for the first derivative. We got to set this equal to 0. So what's nice about this is that we can, when we simplify here, we can get 4x cubed minus 4x minus 4x cubed. These x cubes cancel out. So we get negative 4x over x squared minus 1. So what's nice here about a fraction is if I take 0 and I divide it by anything, I'm still going to get 0, right? So what's nice about this, about first derivative and set it equal to 0, is I only care about the numerator of that first derivative being 0. So all I care about is what is the x that makes this 0. And that would be 0. So that's what's nice about the first derivative on fractions, is all we have to do is take that numerator and set it equal to 0. Okay, so there's our x. So that is our x that we're going to put on a number line, 0, and then we're going to test to the left. So I want to plug in -1 and then test to the right. Let me use a different color here. And a +1. Okay, this kind of stinks too because you have to set it into the second derivative. So I have to plug 1, and those aren't going to work, right? Because I know those are undefined. Well, yeah, I know those are undefined, so those aren't going to work. So I got to try something else. Oh, sorry. What you need to do is also put those on a number line. 1 and -1. And then we're going to test in between here. So I actually need to test like -0.5 and 0.5. So the only thing different about this one is when you find those x's, you got to take those x's of that first derivative and your vertical asymptotes, and that's what you got to test in between. So -2 and 2. So I got to test all the blue ones there. So those are the ones that I'm going to test. I'm going to test them in the second derivative, which kind of stinks, but when I plug in -2, I know this on bottom, whatever's on bottom, is going to be squared, so I know it's automatically going to be positive on bottom. So no matter which ones I plug in here, it's going to be positive on bottom because I'm squaring. So really all I need to do is put them on top, okay? And this is mostly going to happen because aren't you always going to have a squared on bottom because it's g squared on bottom? So really what's nice, only have to worry about the numerator. Okay, so I plug in -2 into the numerator, I get a positive, so that means this is positive. When I plug in a -1/2, I still get a positive. And when I plug in 1/2, I get a negative. And when I plug in 2, I also get a negative. Okay, so there's how it goes. That's how it looks. So what that tells me is that because I went positive, positive, there's no max or min there. And when I went negative, negative, there's no max or min at 1. So that means I just have a max because I went from positive increasing to decreasing. So that means I have a max at 0. So I have a max at 0. And then, so I have a max at 0. I have my vertical asymptotes, my horizontal asymptotes, and I have my max. So now what I need to do is I need to take the second derivative, find concave up and concave down. So here's my first derivative, right there. And then I want to take the derivative of that. So this is going to be my f, and this is going to be my g. I have to take the derivative of f, which is -4, and then I have to take the derivative of g, which is chain rule. So we get 4x times x squared minus 1. If you wanted to, you could distribute that. Okay, so now I go ahead and take g which is x squared minus 1, and I times that by, squared, and I times that by f prime, which is negative 4, so I'm just going to put that out front, and then minus g, which is x squared, g prime, g prime, which is 4x, times x squared minus 1, and I'm going to times that by f, which is negative 4x, all over g squared, so that'd be the bottom squared, so that'd be to the 4th. Okay, then I can start simplifying this. This I could go ahead and FOIL out, so that is x to the 4th minus 2x squared plus 1 times by negative 4, and then minus, well, a negative 4x times a negative 4x is a positive 4x, or 16x, times x squared minus 1, all over the bottom to the x squared minus 1 to the 4th. So we could do a couple different things here. I could distribute that, simplify the top, which is fine, or I could really have factored out an x squared minus 1, because in both of those I have an x squared minus 1. So I could have factored out that would have been gone, factored out one of those, it would have been gone, and then I could cancel out one of those, and that would be cubed. So I could have did that. I mean, I still can kind of down here. That might be easier, then you wouldn't have to FOIL that out, but I kind of already did. So anyways, you still get the same answer. So this is 16x cubed minus 16x, so I'm not going to do that. I'm just going to keep on working here. Negative 4x to the 4th plus 8x squared minus 4 plus 16x cubed. So this all over, and then I can combine some like terms here if I wanted to. Nope, no like terms there. So again, when I take the second derivative and I set it equal to 0, I really don't care about the bottom at all, because I know anything on the bottom to the 4th is going to be a positive, right? And when I'm looking for setting this equal to 0, I just care about the numerator being 0, so really all I care about is just the numerator being 0. Plus 16x cubed, I'll put them in order, plus 8x squared minus 16x minus 4. It's kind of big. So then all I care about is that numerator. Real quick though, this should be a 4th, right? Because negative 4x times negative 4x is 16x squared, so this should be a squared. And this should be distributing, should be then not to the 3rd, but to the 4th. So then I can kind of combine like terms here. So I'm going to take that numerator, set it equal to 0. So I get a positive 12x to the 4th minus 8x squared minus 4. So I can factor out a 4. And so we get 3x to the 4th minus 2x minus 1. So we go ahead and set that equal to 0. Don't forget my squared there. Set it equal to 0, so all I care about is when this is 0. So this is in quadratic form. So I can take this. I don't care about that 4. So I just care about this. Set it equal to 0. So I go ahead and use quadratic form, so it's like a quadratic formula. This is my A, this is my B, this is my C. So I could just really factor it. I could use cab. Negative 3 is my CA, my B is 2, so negative 2. So that means negative 3 plus 1, and then divide those by my A. So you could use quadratic form if you want to. So x minus 1 and x 3x plus 1. But my x is not x, it's actually x squared. So This is really x squared minus 1. And this is 3x squared plus 1. So basically what I have to do is just square root these x's here. So x squared equals 1. Square root, I get plus or minus 1. And then square root negative 1/3, which I can't do. So then that's not going to work. So then I just have plus or minus 1. So then I put plus or minus 1 in on a number line like this, and I test points in between. So I'm going to test points -2 and 0 and 2. So I'm testing points into my second derivative. So I'm going to plug those back into my second derivative, which again, I do not care about the bottom because that has a degree of 4. So I do not care about the bottom. So all I care about is this top, which is just 3x to the 4th x squared minus 1 right here. So that's all I care about plugging in those numbers. So I'm going to plug them in right here. So I plug in -2. That's to the 4, so that's a positive. That's a positive. But I have a negative out here, so that's going to be negative. This is going to be positive. And that's going to be -1. So better thing was we do factors. So let's write the factors. We had 3x minus 1 and an x. So these are both squared and plus 1. No, minus 1. And that was a plus 1, sorry. Okay, so if I plug these back in here, I'm going to square this -2, and it's not going to matter, right? So I get 4 times 3, that's going to be positive. Plug in, that's going to be positive, so this is positive. Plug in 0, that's positive. This is going to be negative, right? Because when I plug in 0 there, so positive times a negative is a negative. And then this, plug in 2, same thing as plug in a -2, I get a positive. Okay, so then I'm concave up from -infinity to 1, and I'm concave down between -1 and 1, and then I'm concave back up from 1 to infinity. So then my graph looks something like this. So here's what my graph would look like. So between -1 and 1, I was concave down, and from -infinity to -1, I'm concave up, and then I was concave up from after 1, and those positive and -1 were vertical asymptotes, and then my horizontal asymptote, so I graph horizontal asymptote, vertical asymptotes, and then I put in my concave up and concave down. Now what I might want is maybe some points, right? So I might plug in after my vertical asymptote and before my vertical asymptote, and then in between I might plug in a point, so then I can find out kind of where my graph is. So that's kind of how you do those. Kind of tough, but I'll also give you a paper with kind of the steps on them to do it. Okay. So it's a little tough, but